So this is the lecture on the definite integral and area part 2, and in this lecture we want to start with the definition. So last time, if you remember, we talked about this definite integral, the integral from a to b of f of x dx. We named these various parts, so let me remind you what this says. And so this is said, the integral from a to b of f of x dx. And a and b are called limits of integration. B is the upper limit, and a is called the lower limit. So b is called the upper limit, and a is called the lower limit. And you can see how when we say this, the integral part is this. Of course, from a to b are those limits I highlighted in yellow, and then f of x, of course, is right here, and this is called the integrand. So normally we refer to f of x as the integrand when we're doing integrals. And then, of course, dx is on the end. So dx and dx. And hopefully you remember, when I say integral, you say area, because this is what it actually means. So this is equal to, so the concept is that this is the area underneath the curve from a to b. And so if you had a picture here of f of x, so this is my f of x, and this is my a, and this is my b, this definite integral will actually be a number, and the number is this area underneath the curve here. And so that's the big idea. Today, and that's what we did last time, really, and we used this left-hand sum, right-hand sum, and midpoint sum, these rules, left-hand rule, right-hand rule, midpoint rule, to estimate what this area might be using rectangles. Today what we want to do is I want to give an actual definition. So we're going to step it up a bit, and I want to define the integral, the definite integral, give the actual definition of this, f of x dx. This is similar to giving the definition in some way to the derivative. So if you remember, f prime of x was equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. So that's one definition that you should know. That's for derivatives. The next one is for integrals. And to understand this, let's go back to the picture. So let me draw a nice big picture here. And so here's my f of x. And the idea is you're going to start over here at a, and you're going to end at b. And if I want to approximate this definite integral, one way to do this is to split up a and b into n pieces. All right, so I'm going to split up this thing so I get this delta x for each one equal to b minus a. That's the length of the interval divided by n. And you'll split it up into n pieces. We'll call this x sub 0 for a. And we'll go over a little bit more. We'll call this x sub 1. We'll go over a little bit more. Call this x sub 2. A little bit more. Call this x sub 3. And so on until we get over here. We'll call this x sub n minus 1. And we'll call b x sub n. So the idea is to split this interval up into pieces, just like we did before when we're doing this left-hand sum, right-hand sum, and midpoint sum. we'll split it up into these pieces, and we'll find these various rectangles. Now, to find these various rectangles, instead of picking a specific point like the left endpoint, the right endpoint, or the midpoint, we'll pick any old point you want in here. So we'll call this C sub 1. And any point you want in here between x1 and x2, we'll call it C sub 2. Any point you want in here, it doesn't matter as long as it lies in between the interval. And we'll go all the way up to here, and we'll get C sub n. And then the idea is that this input has an output on the graph up here, which is f of C1. And so we can make this little rectangle. And we can do the same for C2. So we have f of C2. And we can, again, make another rectangle. And then we can do the same for C3. So we have f of C sub 3, and so on. Right, so dot, 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 rectangles all in between. And then we have f of C sub n. Now notice we didn't rely on the left endpoint, the right endpoint, or the midpoint. All we basically did was chop these intervals up into pieces, and then we can add up all these rectangles. And so what we get here is we get that this is approximately the sum, and this is just a notation for sum of something. And so we don't have to write these all out. So let me write them out first for you, so you can see f of C1, and then we have delta x plus f of C2 delta x plus dot, dot, dot plus f of C sub n delta x. And so we could write this in a nice sort of short closed form, so we don't have to keep writing it out, as we draw the sigma here, and we'll do f of C sub I delta x. Again, delta x is the length of these little intervals here, found by taking b minus a divided by n. So it's the number of rectangles. So notice there's 1 rectangle, 2 rectangle, 3 rectangles, and n rectangles. And we'll start from I equal to 1 up to n. We use I is called the index. So if you understand the idea of an index in a book, you look in the index to find a term inside the book. So the index here is the same idea. It just starts at 1. So there's 1. Then if I is 2, you get this one right here. It's C sub 2. And when I is n, you get C sub n. So it's just a closed form for this sum. All right, so it's approximately equal to this. Now, to get equality, the idea is you have to take more and more rectangles. So to get equality, all you need to do is say this is actually equal to, then to get equality, more and more, take the limit as n goes to, well, what's more and more? Hopefully you say more and more is go to infinity. So let the number of rectangles go to infinity. And then this is the actual definition of the definite integral. Okay. Understand the idea. All you're doing here, is adding up areas of rectangles. So f of C sub I delta x is just the area of any general rectangle. So you do the first one, the second one, the third one, the fourth one, the fifth one, and so on, all the way up to the nth one out here. And as you take more rectangles, you get a better and better approximation to this actual area if you want underneath the curve. And that's how we define this definite integral. Now this sum has a name. This sum right here, typically we refer to this sum as the Riemann sum. It's named after Riemann. All right, the Riemann sum, a famous German mathematician who first wrote down the definite integral in this way, using this type of sum. Okay, so let's make sure I have all this here. Let's zoom out a bit. I gave you everything I really wanted. So first on top here we have the conceptual idea. I say integral, you say area. And then down here in blue we have the actual definition of the definite integral, which is just basically add up all the rectangles. Now, there's something happens in this definition if your function's negative. So notice, and we're going to take a look at an example here in a minute, that there are certain properties that are going to occur here. So if your higher function's negative, this definite integral is actually going to be negative. So this is not always going to be interpreted as area given this definition, which you'll see in the next example. But it does have nice properties. So a couple properties of this, which we're going to see here in a minute. Right, so properties of this integral. It turns out if you add two functions, like suppose you take the integral from a to b of f plus g dx, this is the same as the integral from a to b of f of x dx, so it's just write f dx, plus the integral from a to b of g dx. So the integral goes through addition and it goes through subtraction too, so whether you're adding or subtracting, it does not matter. It also, you can pull out a constant, so that's probably the first rule here. If I have the integral from a to b of, let's say, some constant k times f of x dx, you can actually pull out the constant here. So this is k times the integral from a to b f of x dx. That's also a nice little property. And there's one more property that we sometimes use. It's sort of strange. We don't use this too much, but the integral from a to b of f of x dx is actually equal to the negative of the integral if we flip or swap the limits of integration from b to a of f of x dx. So that's kind of a nice little property that we can sometimes use. But these are some of the basic, let's just write this as basic properties of the integral. So let's take a look at an example of how we can use this, sort of the consequence of this definition. And so here's our first example, and we want to use the picture to answer the following question. It's the integral from a to b of f of x dx. So here's a, and here's b, and so I say integral, you say area, so it's just equal to this area underneath the curve, which it says is 16, so that's pretty easy. Now from b to c, let's switch colors here. So now from b to c, here's b, and we're going to go to c. Now here the area is 2, but it turns out that this answer is not 2 because the height of the function is negative. And so this turns out to be positive 2, but negative 2. And again, this is a consequence of the definition. If you look at the definition again of the integral, it's just equal to the height. So if the height is negative, you're going to get a negative value out for this definite integral. And now let's look at from a to c. So let's erase this here so we can then look from a to c. So here's a and here's c. Now again, I say integral, you say area, but you have to be careful, okay? So yeah, the integral from a to c, it's this area, which is 16. And then you have to be careful. You can't add this area. You have to actually subtract it. Because again, the height of the function is negative. So this would be 16. And this would be then minus 2, which would equal 14. So although, yes, the integral does produce in some sense area, it's not going to be always the number we would expect. Because if you said, what's the area underneath this curve, I'd actually say it's 16 plus 2, which is 18. But because this definite integral doesn't understand that the area always needs to be positive, it's going to take this 16, and because this height is negative, it's going to count this as negative. This area is negative 2, and it's going to subtract. So 16 minus 2 is 14. Now you can undo this by taking the absolute value. So remember, understand what the absolute value does to the graph of a function. It simply makes whatever's negative, and it makes it positive. So like over here, if you take the absolute value of f of x, this is already positive, so it'll leave it alone, but it'll flip this and make it positive. And again, that area is just 2. And so what's going to happen is the integral from a to c, it'll take 16, and now it'll add 2, and so you'll get the actual area underneath the curve, which is 18. So be careful. When the function goes negative on you, the integral is going to count that as being, negative quote-quote area. So it won't add, it'll actually subtract. Let's look at another example here where we can use these properties of the integral. So I want to find this integral from 30 to 70 of f of x plus 2 g of x d of x. Well, I know by the properties of the integral that the integral will go through multiplication. So this is the same as the integral from 30 to 70 of f of x dx plus the integral from 30 to 70 of 2 g of x dx. And I also know that I can pull constants outside of the integral. So this is then going to be equal to the integral of 30 to 70 of f of x dx plus 2 times the integral from 30 to 70 of g of x dx. And so what we're going to do is we're going to find this integral of f of x from 30 to 70 and this integral from 30 to 70 of g of x, and then we'll multiply that one by 2 and add them together. So let's take a look. All right, but first we'll find 30. So here's 30 right here. And of course 70 is over here. If we do, let's do f of x first. So the idea behind f of x, and we can do this in green, we want to go from 30 to 70, and here's f of x, it's in blue. And so from 30, it's just the area underneath this curve. So it's going to be this region all the way to here. And the way you do this, to find this area, and it's going to be negative, right? It's actually pretty simple. I'm going to split it up into two nice geometric figures. And if you see here, I'm making a square and a triangle. So this square is 2 by 2, so it has 4 blocks. And each block, notice each block has area 100 because it's 10 by 10. So this right here is 4 blocks of 100, and so that's 400. So in black, let's just write it right there. It's 400 square units. Again, there's 4 blocks, 1, 2, 3, 4, and each block has 100 for its area, 10 by 10. And so that's 400 square units. And of course, this is half of those 4 blocks, so that's 200 square units. And so the first term is 600 plus 2 times. All right, so that was 600 plus 2 times. Now to figure that out, I need to erase this. So I'm going to erase this right here. I'm going to fill this back in. So again, I'm going from 30 to 70. So here's my 30, and here's my 70. Now I'm looking at this red region. So let's take the green out. This red graph, and then from 30 I have this piece here, and then it goes negative, and then to 70 it goes all the way down here. So interesting, I have 2 triangles exactly the same size. The integral is going to see this area as positive and this area as negative, and so these two things are going to cancel, and you're going to be left with 0. So just think about it. I mean, I can calculate these areas if you really want me to. And let's do it. It's a nice exercise in geometry here. So what we have is a triangle, and it's made of, you have 2 squares here, and you have 3 here. So you have 6 squares for this whole rectangle here. And so you divide it by 3, so you get 3 squares here. Remember, the area of one of these little squares is 100, 10 by 10. And so if you have 3 of them, what do you get? You get 300 here. So the integral will count that as 300, whereas here the integral will count this as minus 300, and if you add them together you get 0. So this is just going to be equal to 600 units squared. Using the properties of integral. And of course I say integral, you say area. You just have to watch out. If it falls below the x-axis, if the graph falls below the x-axis, the definite integral is going to count that as negative. Okay, so how do we evaluate definite integrals? Well, one way to do it, which we've been doing here, is just consider it as area. We can also use technology, which we'll do in a minute. We'll use our calculator. And then finally, we're going to conclude this lecture with the fundamental theorem of calculus, which tells us how we can do this by hand and incorporating our knowledge of derivatives, because it turns out that integrals, definite integrals, and derivatives are intimately connected. But let's look at the next example. So trying to understand how we evaluate definite integrals using area. And so on this one, it says evaluate the definite integral by interpreting it in terms of area. So what we'll do, we'll start with the is we'll draw a graph to see what this actually means. And so 4 minus 2x, this is my function, f of x equals 4 minus 2x. And now it's a nice line, so I really don't need my calculator. I know if I plug in 0, I get out 4. So 1, 2, 3, 4. So I know this point 0, comma 4 is on my graph. And I also know if I plug in 2, I'm going to get out 0. So 1, 2. So 2 comma 0 is also on my graph. And it's a nice line. So you simply need to connect the dots. So this just connects the dots. It's a nice looking line going through those dots. And if you want to find the integral from 0 to 2, right, I say integral, you say area. It's just the area underneath the curve given by that blue shaded region. And so this is pretty easy to calculate because this is just a nice right triangle that has a base of, what, 2 and a height of 4. So remember, the area of a triangle is given by 1/2 base times height. And so then this area is 1/2, the base is 2, so times 2, where the height is 4. And so this is just equal to 4 units squared. And so that's what we mean by evaluate the definite integral by interpreting it in terms of area. So evaluate's a fancy word for saying, hey, what does this thing actually equal? All right, and so now in the next example, instead of using geometry, we can use technology to do this, and that's actually a lot simpler. And so let's take out our calculators here. And just like we did in the last lecture, you can simply graph the integrand and then use your calculator. And so let's get rid of this. And so we hit y equals, we'll graph the integrand, 4 minus 2x. And it's easy to make the window. The window is going to go from 0 to 2. And then we'll zoom fit it. And you get a nice looking graph. Now, if I do this, I always like to graph it on the page here. It went down like this. I'm looking for between 0 and 2, just to remind myself what I'm actually doing so I don't just follow this process completely mechanically. This turns out to be 4. And then I can take second trace and then go down to the integral of f of x dx and hit enter. And of course, the lower limit is 0, whereas the upper limit is 2, and I'll shade that region in and spit back the answer of 4. So it should agree with our last. So this is 4 units squared. So that's a nice way to do it. There's also a way to do it on the clear screen, actually. If I'm going to show you this, I usually just graph it. That way I have, that way I can see what I'm actually doing. But if you hit math and you hit scroll down, you're going to find this FNINT integral. So that stands for finite integral, which is definite integral. If you hit enter, and then some of the newer versions, it's going to look like the actual integral on the screen. It'll actually look like more like this. Now mine's old school, so I have to enter it like this. So I could enter 4 minus 2x, and then I'll put a comma. And I'm trying to remember, I think I put x next when I'm integrating with respect to, comma, we'll find out here in a minute, 0, comma 2. Right, those are my lower limit and upper limit. If I hit enter, it spits back the answer 4. So this is the integrand. This is what I'm integrating with respect to, and then 0, comma 2, which gives me 4. And in the newer calculators, it's even better. It looks just like this. So you just use your arrows up and down to change the limits of integration. Put your integrand in there and plug in the x after the d, and you'll get back 4. All right. So now this is actually sort of a big deal in calculus when we talk about this fundamental theorem of calculus. What the fundamental theorem of calculus does, and we're going to see this later, is it actually gives rise to new types of functions. So new types of functions. And when I say new types of functions, what I mean are functions that can't be expressed in terms of the elementary functions we talked about before. So if you go back to the beginning of the semester, we talked about these elementary functions. So these elementary functions. And the idea is that most of the functions that you've seen can be made out of these elementary functions, and there's 4 of them, 1, 2, 3, 4. And the first type of function is a power function. The second type are exponential functions. The third type are logarithmic functions. And the fourth type are trig functions. And so these are, real simple little functions. So like x to the n, e to the x, ln of x, and then cosine of x, sine of x type stuff. And most of the functions we work with are made from these by adding, subtracting, multiplying, dividing, and composing. Well, it turns out that integrals will give rise to new types of functions that can't be expressed in terms of these. And that may not seem like a big deal, but it's a huge deal. I often tell students it's sort of like discovering that dinosaurs existed in some sense. It's really a huge deal that we can give, that this integral gives rise to these new types of functions which we didn't know about before. And you'll see them, especially engineers and your various majors, you'll see these sort of special functions later on. And we'll talk about them a little bit later. But for right now, we want to talk about just the start of this fundamental, the sort of basic idea behind this fundamental theorem of calculus. And it really does, it's going to give us a way to do these definite integrals by hand. So what does it say? So let's suppose f of x is continuous. So continuous on AB. This closed interval AB. All right, then what we know is that the integral from a to b of f of x dx is equal to, and I'll tell you what this is capital F of b minus capital F of a, where capital F is the antiderivative of little f. All right, i.e. f prime, capital F prime of x is equal to little f of x. So now this is a huge deal. So, and we're going to talk about why this is true, and it's going to take us a little while. So if you have a continuous function and you look at this definite integral, you can evaluate it by finding the antiderivative of little f. So let me do a quick example right below this so you can see how this theorem works. So this is called the fundamental theorem of calculus, and we're going to call this one part 1, although in the book it gives you a slightly different version. They actually call this part 2. We're going to call it part 1 because we're going to use it. It's the first part we're going to use. But let me give you an example. If you do the integral, let's say from 0 to, let's do 3, of 2x dx. Now my calculator will tell me what this actually is. So I can take out my calculator and I can plug in my y equals, and I can make this equal to 2x, and I can make my window go from 0 to 3, and I can zoom fit it. I don't even need my calculator to do this. I can also use the geometry because this is a triangle. But I can hit second trace and go down to number 7, which is the integral, lower limit z, lower limit 0, upper limit 3. And it's going to shade this in, and it's going to tell me it's 9. So I know the answer is 9. So I know this is equal to 9. But I can use this fundamental theorem of calculus to tell me this if I can find the antiderivative of little f. So let's just look here. Can you tell me the antiderivative of 2x? Can you tell me a function whose derivative is 2x? So think about the question. Can you find a function whose derivative is 2x? And hopefully you say, okay, what function when I take its derivative do I get 2x? And you say x squared. So what we'll do is we'll write x squared here, and I'll keep these limits evaluated at 0 to 3. Right, so this is like my capital F. And then I'll plug in the limits of integration. So I'll plug in a 3, so that's 3 squared, minus, plug in the lower limit, 0 squared. And like magic, you get back 9. Okay, which certainly agrees with the answer. Now, why does this work? Why does this work? Why is the derivative and the area connected? Right, why is the area connected, right, to the derivative? And this is something we're gonna work on a little bit. Next time when you come into class, I'm gonna give you a little sort of PowerPoint presentation to try to help you understand why this antiderivative, why the notion of derivatives and area are actually connected. And we'll talk about that next time. But for now, let's just look at our last example, which is the same one we did before. Okay, so we know that this answer is equal to 4, because we just did it in example 4 and example 3. But we want to use the fundamental theorem of calculus to do this. So let's just copy this down. I have the integral from 0 to 2 of 4 minus 2x dx. And so this is going to be equal to, I have to think, do I know a function whose derivative is 4? And hopefully you say, oh yeah, I do. That would be 4x. And then minus, do you know a function whose derivative is 2x? And you say, oh yeah, x squared. So the derivative of 4x is 4. Derivative of x squared is 2x. So you get 4 minus 2x when you take its derivative. And you're going to evaluate this from 0 to 2. And so the fundamental theorem says if you found an antiderivative, you simply plug in the upper limit. So I plug in 2. So 4 times 2 minus 2 squared. I'll put parentheses around that. And then you subtract off when you plug in the lower limit. So 4 times 0 minus 0 squared. And so this is going to equal 8 minus 4. And of course, this term is minus 0. And I'm going to get back 4. Notice, again, this is what the fundamental theorem tells me to do. Up here, let me write it down again. The fundamental theorem of calculus basically says the integral from a to b of f of x dx. How do you figure out this definite integral? By hand. All you need to do is find the antiderivative of this thing. So find a big F, which is the antiderivative, plug in the upper limit, and then subtract off when you plug in the lower limit. And big F has this property, when you take its derivative, you get back F. So look how this corresponds. Right? So you find the antiderivative and you plug in the upper limit. So here's the antiderivative, and here's where you plug in the upper limit. Right? So these two things are connected. This theorem tells you to do basically this. Find the antiderivative and plug in the upper limit. And then you take off. So you take off here, subtract. So you subtract. And then you plug in the lower limit into your antiderivative. So I plug in my lower limit to my antiderivative. And then I crunch the numbers, I do the arithmetic, and I get back my answer of 4. And so that's how we do these definite integrals by hand using the fundamental theorem of calculus.